All right. So all that being said, let's go. Let's talk about turbulence with our time. So, what did we talk about last time on this list? I'll give you the. You even boil it down to that. How far did we make it? Just the first one. Exactly. So we have a little bit of catching up to do in this part, and I've actually added a bunch more about doing this for real based on these theories. But we're going to push in and try to get through this, and then on Friday we'll get the rest of the way through. And then next week I plan to start talking about Thorpe. So if you haven't taken a look at that, you can take a look at that. We'll follow through the first 3 chapters of Thorpe. They're short. Next week. So we'll talk about real ocean turbulence, how it's observed, and you'll see that a lot of the concepts from this discussion will appear in that discussion, but pieces won't. So that's where we'll be for next week. Okay, so we talked about averaging. I don't want to dwell on this too much. We talked about this. Okay. This is sort of an interesting, so we're going to talk more about this at the end, but if you use a Reynolds average, so how do we define Reynolds average? It was one that if you take the average of the average, you get the average, which is not the same as a filter, where if you apply a filter twice, things get smoother still. So that's a property of only some kinds of averages. You can actually break down the kinds of simulations we do in oceans and atmospheres into Rand's average, Navier-Stokes. They might also have Boussinesq approximation or hydrostatic approximation on top. But you can do that for the mesoscale, or you can do that for the submesoscale. So we have this complication that relative to what length scale? What's our key length scale? Deformation radius. So if we resolve the deformation radius, we're going to resolve the instabilities. So there's a mesoscale deformation radius and a submesoscale deformation radius. And so once we know the resolution of our model and those deformation radii, we'll know whether we're permitting those things to occur or not. So if we're not permitting them at all, if we're very coarse resolution like climate model style, then we might use a Reynolds average, have all of the mesoscale eddies and all of the submesoscale eddies all have to be parametrized somehow. And so you might call that MORANs or RANs, but mesoscale ocean RANs. If you allow some of the mesoscale eddies, but not all of them, and then you use a filter as your definition, then you're kind of in a large eddy simulation regime. So large eddies means the biggest ones are resolved, the smallest ones aren't, and then you really want to use the filter style rather than a Reynolds average style, because there's not a clear place to put the Reynolds averaging scale, and so it's better to be kind of flexible and keep the filter approach in. And we'll see how this all goes later. And you can do the same for submesoscale and the same thing for boundary layer. So in that little movie in the beginning, we're actually seeing a boundary layer large eddy simulation on the right hand side. So that's one where we're resolving the largest eddies, the largest Langmuir cells. That's one example. And we'll see lots of other movies and see that part. So the reason why this matters is because the way you treat the things that are not resolved depends on what kind of model you're thinking about. So if you're thinking about a Reynolds average model, then you could take a Reynolds average approach. You could have the Reynolds stresses and the mean contribution, and those two together would go into your mean equation. For all of the linear terms, if you choose the average right, you can commute the averaging and the differentiation, and then you would have, so all of the normal terms just basically get converted into terms for the average equations, but the nonlinear terms, you need an extra bit of help to represent the turbulent effects. Everybody, does that make sense to everybody based on this Reynolds averaging concept? And if we're using a filter, we still need to do this, but we may not be able to, it may be complicated to think about what prime means. And so I will write the least interesting equation in turbulence closure theory, which is if what we want is this, And what we have is this. We need to write a parameterization, a subgrid closure, an eddy diffusivity or eddy viscosity kind of thing that gives us this. Okay, so this is the world's worst equation because this just cancels this and this cancels this. So there's almost no information content in this equation except for these parentheses. And the parentheses are important because we're thinking of this combination as a block. This is what you need to parameterize in order to capture the important aspects of turbulence. This is what we have, this is what we want, so we have to build a parameterization to give us the difference. Okay? And so, if I was in the case where I have a Reynolds average, then I know that this part would have one part that was like, if Reynolds averaging, then I know that U tau bar equals U bar tau bar plus U prime tau prime bar. And then I could plug this into there and this would become U prime tau prime bar if Reynolds average. So in the special case of Reynolds averages, we could write it like this. But in the more general filter case or not, we actually don't know what this is, so we have to think hard about how to get it. Does that make sense to everybody? What the distinction I'm trying to make is? Okay, so we talked about Reynolds stresses. I'm not going to talk about that. Okay, so how might we do something like this? So turbulent diffusion or turbulent viscosity, both are examples of a closure, which is a way of writing this unknown thing in terms of things that you do know, plus some guesswork. So that's what we need to do if we have a model that doesn't resolve the turbulence, all of the turbulence. So either a Reynolds average or a large eddy simulation. We would try and construct an approximation to this based on things that we don't know. And we actually have already been doing this because in all of continuum mechanics, even at the beginning when we wrote viscosity and diffusivity for the Navier-Stokes equations way back when, what does that actually represent in the physical world? Molecular forces, it's an approximation, it is actually an approximation, it's not exact, to the effects of non-continuum things, motion of molecules, on the continuum. Does that make sense to everybody? So when molecules move around, they carry properties with them. We can't express that in a continuum mechanics sense because the molecules are not continuous. So there is already built into the idea that you'd write a viscosity or a diffusivity an approximation about those molecules. The concept of a turbulent diffusivity or a turbulent viscosity is essentially treating turbulence the same way. Pretend that the eddies are like little molecules and follow through to get an equation out of it. So let's see how that goes. So here's the molecular diffusivity. Here's an equation for conservation of something, whatever. This could be salinity or potential temperature or density, whatever. If we take the Reynolds average of it, we get the partial derivative of time, the Reynolds average commutes with that, and then we have the parts that are resolved, so the Reynolds average double fields, this side, this piece, and we need the other piece, which is this part, which is basically just the prime versions of these. We don't know what these are, right? So what we mean by a parameterization or a subgrid closure, or lots of different phrases for it, and we'll, as we start thinking about how to build these for the rest of the semester, I'll get a lot more specific about which is which. What if we pretend that these two have the same form as this? That's an eddy diffusivity. So there's a big K instead of a little kappa. It's big because we normally think it's bigger. We'll come back to that in a second. And see, the prime parts are coming, it's depending on things that we know and something that we need a theory for, or we could just leave it as a tunable property and say, whatever that is, we make it like this. So this, doing this like this, is treating the eddies, essentially, exactly like they were molecules, assuming that the form of this closure looks like the form of this. It has some really nice properties. We don't create or destroy this conserved thing. We just move it around with this diffusivity, which is a really nice characteristic to have. I could write a different form in which that would not be true. But we don't know what this big K is. So we can spend a lot of time thinking about what it is. Vallis gives one quick example where he says, suppose we think of this prime here as being a length scale times the large scale gradient. So if I had a gradient of stuff, you know, where it's big up here and small down there, and I displace this, I could say that phi prime was approximately the distance that I displace it times the gradient. dy. Does that make sense to everybody? Because the anomaly here is about, gets bigger the farther you push it from what your neighbor is. So that's the idea behind this relationship. This thing is called a mixing length in this theory. And if you just plug in this form into there, you get something that looks an awful lot like this, where the kappa is the velocity perturbation times the mixing length on average. Okay? There are a lot of problems with this, yeah.
Can I ask why U is inside the material derivative?
Why, which is which?
At the beginning it's the material derivative.
Yes.
And then we are looking at the advection term.
Yes.
I think U is not in the derivative.
And this doing?
No, I mean the spatial derivative.
Here?
Yeah, dy.
Oh, he's assuming that it's incompressible form. So he's bringing it in. So sorry, it's a little weird in 2D. In 3D, well, this is the big question: is U dot grad phi, is that equal to divergence of U phi? Well, it is if. So this if I just differentiate it out, is phi divergence of U plus U dot grad phi. And if this is 0, then that works. If it's not 0, then you have to be much more careful, and then you get to get from the flux form to this, you have to be careful. There's a density drifting around, essentially. That makes sense? Yeah. But it's convenient to write it this way because it puts the things you want to average together next to each other. So people frequently do it, but technically to write it this way, you do have to have either a divergence term on this side that you also need to handle, or keep the U outside. Does everybody follow what Yingshi's question was about? Okay. All right, so what's the problem with this? What are some problems with this? I'll give you the simplest answer. Is this a reversible or an irreversible process? Like in the thermodynamic sense. If we take something and diffuse it, does it undiffuse? Not unless we have negative diffusivities, right? Is this a reversible or an irreversible process? Or is this? So let's think about this anomaly. What if it's wave-like and it just keeps oscillating? but the wave never breaks. Is it reversible? Yeah. It goes back to the initial state twice an oscillation. So this assumption only works if this L is not just a temporary displacement, but it's actually a permanent displacement. So to be a little more precise, we shouldn't just think of it as like this, we should think of it as, what if that blob separates off and keeps going? So it is perhaps a little more precise to say L is the decorrelation distance. It's the distance over which the turbulence moves and becomes decorrelated with where it started out. So, or to put it another way, if it was a wave, the wave would need to break to make this permanent. Or if you were in a wave in the presence of a restoring force, there's a more complicated form of this. But you need an irreversible process to make this closure make sense.
So L is not a constant. It's a function of time or something?
So L is just measured a different way. You shouldn't just take the anomaly if the anomaly goes back to 0 a little while later. You need to find L as the distance over which things move and then forget and never go back to where they come from. So if this little blob goes up and then separates into an eddy and doesn't go back, then this L is actually a good one. Does that make sense?
So it's a length scale.
There's a length scale. There's also a time scale of decorrelation and turbulent flows. You know, like blobs are getting shot off everywhere. You need to describe the blobs, not the things that go back to their initial condition, in order to make the assumption that we're really only talking about the irreversible part when we switch to this, not the reversible part, which is also included in this. Yeah.
But if this is screened by external source, like a heat engine, then this can still work.
It does, because this has both. The difficult part is what this value is actually what happens in the real full resolution fluid is things break off. They're stretched out by turbulence, and then that stretching actually triggers some of this to go on, but not on the mean, on the little filaments. So what we're putting here, this big K, in some sense, should depend on the little k. Because if you turned off the diffusion altogether, it would be much more difficult to have irreversible motions. Whereas if you had a lot of real molecular diffusion, it'd be pretty easy. Even wave-like perturbations would be damped after they get perturbed out. And so you would get irreversibility out of this part. So, and you can get very deep and philosophical and wonder about the arrow of time and all this stuff if you want. But the point is turbulence stirs stuff up, and then diffusivity mixes it up, and you forget about the initial problem. And we don't tend to reverse that process in really turbulent flows. In linear instability theory, you can solve for all kinds of things, and you get a very strong dependence of the amount of this stuff based on this. So in weakly linear or quasi-linear theory, for those of you who've been talking to Brad, that's very strongly impacted by this value. But in fully turbulent flows, in the sense we're going to talk about in just a minute, there's something called an inertial range, which is a range where this is behaving irreversibly, but it doesn't depend on this. That's the idea. Okay. And this is just the analog that we talked about before about eddies versus molecules. I go through this. If you do it for viscosity instead of diffusivity, this thing is actually a tensor until you make it so it has multiple directionality in it. If the mixing is, say faster in one direction than another, you really should have a kind of complicated operator here. But if everything is isotropic, and we kind of assumed it there too, then you just get a scalar diffusivity or a scalar viscosity out of it. Okay. Last thing I want to talk about before we switch over to talking about the spectral theory is homogenization. So this was actually a PhD thesis that wrote this down. Really nice. Bill Young, who's now at UCSD. This was his PhD thesis idea. If you have a closed streamline and an eddy diffusivity, or even a molecular diffusivity, and you're considering a steady state, what does that say about the concentration of stuff inside the middle? If you assume that there is a steady balance between advection and diffusion, steady balance like this, and again we pulled the V inside, so it's simple, then both sides are actually inside of a divergence. So if you think of it integrating over the area within that streamline, you get this, which is basically the flow through that area has to equal the divergence. So the flow through the area is the divergence of the velocity inside or the velocity going out, and if it's a streamline, that's 0. And on the other side, the diffusion through that streamline is the diffusivity times the gradient of the tracer in the normal direction. So what does that say about the gradient of the tracer along the streamline? If this is equal to this. This side, if I take this balance, this side is 0. So if I want to make this side equal to 0, I have two choices. I can either make the diffusivity 0, or I can make the gradient of the tracer 0. That's it. Those are my choices.
Or maybe
The gradient, there could be a gradient along the streamline, except it's a closed loop. So you can't have a gradient consistently along the streamline. That's the other integral. The line integral of a gradient is the difference between the start and the end. So you couldn't have it on net, unless there was an interesting cross-correlation between diffusivity and gradient. So the logic here is, what does this do? If you want a balance that looks like this, it tells you that you can't have anomalies of tracers inside closed streamlines if the streamlines are fixed in time. Even if the streamlines aren't fixed in time, suppose it's turbulent, but there's still a mean streamline, then we could put our kappa plus big K on this side, use our eddy diffusivity, and we get to the same answer again. So if we're imagining the global ocean circulation or something like that as having mean streamlines, like a gyre, this says you shouldn't have any gradients of any tracer anomalies. There should be no extrema in the mean of anything. So potential vorticity is a very interesting case of this. This says that you shouldn't have any potential vorticity anomalies inside of any closed streamline, which means that you have a really simple quasi-geostrophic gyre circulation that comes out of it. Potential vorticity is just constant. That's it. Now you can solve everything else based on that. So this is a pretty radical notion. It's not actually true in the real world because closed streamlines are actually extremely rare. That's the big exception to this, is that the ocean flow is actually very complicated. And so if you look for closed streamlines, you don't tend to find them. What you find are these weird, spiraling, chaotic trajectories. And so it's not as strong of a constraint as it sounds like, but in places where you do see closed streamlines, and there are few in the world, you really don't see any anomalies in any of the tracers inside. Does that make sense to everybody? Sort of?
So
Yeah.
I think in GEOS we do have a mass phenomenon which can be reflected by the
There is, except the gyre flow is not just a streamline. The gyre flow spins around, but it is also overturning in the other direction. So if you're tracking the three-dimensional flow, you don't actually end up with closed streamlines. In fact, There are a few estimates that show that it's actually a space-filling chaotic trajectory, even the steady in time part. So every hunk of water in the gyre experiences every part of the gyre in enough circulations. So this was a radical thing at the time, but it is actually the answer is so beautiful that it's sort of even more interesting. Like everybody was thinking, how do we get a 2D gyre circulation that makes sense? And the answer is there is no such thing as a 2D gyre circulation. It's really a 3-dimensional fractal. So that's much prettier, I think. Anyway, okay, but that's an aside from our turbulent conversation. Yes.
So it's an isosurface of phi, right? I mean,
Yes.
So, sorry, I just got confused. Phi has to be the stream function?
No, phi, this is just the area of integration is a streamline so that we get this. But phi is any tracer you like inside that interface, inside that area. Whether it's salinity or temperature or potential vorticity or whatever you like. Something that is a conserved tracer, so it has an equation that looks like this. That's the game. The other thing that's also, of course, not true in the real world is that there is no steady anything. So even thinking about the mean circulation is kind of a bit of a dodge. Like, you probably, one thing that could happen in this situation is what if your streamline that you'd like to analyze fills up with stuff, and then pops like a bubble and then starts over. That's totally fine. There is no meaningful steady circulation that you should worry about with that. It totally deviates this, and so you shouldn't really be able to think about that kind of a piece. So the real flow does not have closed streamlines in the mean, and also isn't steady. So there are a lot of problems here in thinking about how this works. That's part of the game. In the few places in the world where this is a decent approximation, it works really well. So there are a couple of water masses that do look like they have closed streamlines, and there are no tracer anomalies inside. Okay. All right, but let's move on to the spectral theory. That's sort of a beautiful idea, the idea that what diffusivity does is it removes anomalies. So let's think about different scales, different anomalies, how that fits in far as turbulent flow. So we have a good handle on turbulence. We can approximate it as a diffusivity or a viscosity. That the tendency of diffusivities and viscosities is to eliminate anomalies, smooth stuff out. We have this Reynolds averaging concept and filtering concept that are all kind of floating around. Let's bring those pieces back together and think about how we might build a closure like this, which is what we'll get to on Friday. But even what do we mean by different eddies on different sizes and how they communicate with each other? So what do we know about the communication in the simplest case? Did it occur in our linear theory, our linear geostrophic adjustment theory? No, all of the wave numbers were independent. But now we're pretty sure that once the nonlinear term starts being active, wave numbers are going to talk to each other. And what we want to explain is how that happens mechanically, sort of kinematically, but also how we might still make sense of that story. Okay, we saw the stirring. 3D stirring looks different from 2D stirring. That's also, don't forget, 3D turbulence and 2D turbulence are qualitatively different. Okay, we've already answered this part. Okay, so even though the wave numbers talk to each other, it's still a good idea to start thinking of wave number dependence, scale dependence of our different flow properties. So if we take the Fourier transform, the Fourier series expression for any of your flow fields, this could be U, it could be salinity or temperature. It looks something like this, where we have an X wave number, a Y wave number, a Z wave number. Then we have an amplitude function that's a function of time, In our linear instability case, we actually put t up there too, and we made it exponentially growing or exponentially decaying. That's actually not a great idea in the turbulent case because that's too simple of a time dependence. So we'll allow the time dependence to be potentially more interesting than those two cases, but we keep these, so we're just separating by scale and space, not in time. And the only reason why we're using a Fourier series rather than a Fourier transform is, so what's the difference between Fourier series and Fourier transform? One is discrete, the other is continuous. How far apart are these wave numbers in a series? So if we have a basin of fixed size, and we have, say, a sampling rate across them, so this is just, we're measuring something, or maybe this is our model. What can you tell me about my ability to talk about spectral things that fit in that box? What's
It have to be 0 at the end.
Yeah, so you have something like they have to be 0 at the ends, or maybe they have to be periodic. That would also be okay if I had a periodic boundary condition. But I have some limit as to the biggest thing I can fit in the box. The biggest thing I can fit in the box is something like this, right? What's the littlest thing I can measure? Something that looks like this, right? It's like going up and down. That's almost the worst one. Sorry, you can't really measure that one, that's all nodes. But the one that's maximum at the measurement points and minimum in between. That's kind of the smallest thing you could possibly measure. Let me draw it. Do the other way. I'll draw a nice sinusoid, and then I'll put the measurement points on after. That way I can make myself not go crazy. Okay, so which one of those limits the high wave number n, and which one limits the low wave number n? Which of these has bigger wave number? The smaller one. And this one has the biggest wave number. I could have also had a constant, so that would be the 0 wave number case. So if I didn't have the 0 condition on the end, but if I had periodic conditions on the end, I could have had a constant. So when we think about the wave number spectrum, there's a limit on this end, which has to do with 2 pi over the size of the basin. And there's a limit on this end, which has to do with 2 pi over the sampling size. And it actually turns out that we normally drop the 2's because your half wavelengths are actually okay, not whole wavelengths, but that's just leave the 2 pi's in because it's confused. It actually takes a lot of thought to get that right. So generally that's what we mean. And if I discretize my wavelengths in between, my wave numbers in between, what's the unit of measure of those? Very close. It's the distance between 0 and this first one that gets repeated. So what sets the resolution of your Fourier series in wave number is the size of the basin. This is totally counterintuitive. If I want to know frequencies really accurately, I should not measure at high frequency, I should measure for a long time. If I want to know frequencies very precisely. If I want to know what very high frequencies are, I should measure very frequently. I'll say that again because it's tricky. If I want to measure the highest possible frequency or the highest possible wave number, I should sample a lot. I should have a small grid scale of my model to get the high K numbers. If I want to measure the distinctions between neighboring wave numbers very precisely, I need a big basin. Those two things come together, and it's just the inverse relationship between K is proportional to 1 over L. It's just those kind of things. Does that make sense? So, okay. So we jump back to here. Now, this is a sum over K. What's limiting the K not being continuous is how big the world is, not how frequently we sample it. In a really big basin, it's a good approximation to not use a sum, but to use an integral. That makes sense. So the difference between Fourier series and Fourier transform is how big the universe is, not how frequently you measure it. The highest frequency that you can measure is set by how frequently you sample. In the limit where both of those things are really, really big, then we just forget about the sums and we start writing everything as an integral. But, okay, so here's an object. So we can do it in Fourier series, we can do it in Fourier integral. What might we like to know about the velocity field? In particular, we might like to know the energy. What does turbulence do to the energy? What do instabilities do to the energy? Or geostrophic adjustment, or any of the things we talked about. Do they change the energy? They can change its distribution, but they don't create or destroy it. It was only the viscosity that really ultimately created or destroyed, or letting things run out of the box. The waves running out of the box let us lose energy. But all of our processes are conserving energy. So talking about the energy contained in this total sum is something that's valuable. So in order to do that, the energy is u squared plus v squared plus w, the kinetic energy anyway, which is this thing times its complex conjugate, e to the ikx minus e to the minus ikx. And because what happens if I take two different k's and try and put them together like that inside of an integral?
You get like a delta function, you get like a thing that oscillates unless they're the same.
Exactly. So the only terms I need to worry about are the ones where the positive and negative exactly cancel each other, because then I get e to the 0, which contributes to this integral non-trivially. So this is a way of writing the energy in each wave number. This is a way of writing the energy over the volume. In Fourier math, this is called Parseval's theorem, where I can take a squared quantity in space and convert it to a squared quantity per unit wave number and get them the same if I sum up over all the contributions. But here's the really powerful thing. What is this guy? This is the amount of energy per unit wave number in that transform. So we've been drawing these things all along. That is the power spectrum. That's the thing that we keep drawing like stuff, and we say there's lots of energy at this wave number, less at this wave number. What we mean is that E of k or E sub k, this little guy. And Vallis uses this notation to write it when it's the continuous form, and this one when he's thinking of it in the Fourier series form. Okay? So here's the continuous form of that. There's one more thing we need to talk about here, and then I want to jump to something so we can see. This is now, he's writing it without a bold k. He's writing it with a regular k. What does he mean by that? He uses bold to indicate vectors, regular script to indicate scalars. What is that? What's going on there? He's assuming that there's no difference between kx and ky and kz. So this is formally a spherical coordinate integral where you've already integrated over all the angles in both directions, and you get a 2 pi r squared correction, or 2 pi magnitude of k squared correction to go to spherical coordinates, and then he just absorbs it into the definition of this E of k. So be careful. This is really a volume integral where we're only seeing the last step in the magnitude of k. And if you don't do that right, you don't get the right units for this thing, because there's that r squared part of the spherical coordinates. Okay? But all that being said, now we've got this E of k, and if we integrate it over all the wave numbers, all the magnitude of wave numbers from small to big, we get the total energy, which in real space is just the integral of v squared, 1/2 v squared over the whole volume. Okay? And now the units for this ballpark, and then we'll switch to think about that in the next game, which I'll give you the little hint on, is if we have this definition of energy as a unit wave number, what if we do some dimensional analysis on it? And we start thinking about how it could depend, how it might vary as a function of scale. Big things have some amount of energy, little things have some different amount of energy per unit wave number. Can we describe that in an interesting way? And this is the great breakthrough of Kolmogorov in the 1930s, I guess. They were written in a series of 2 papers in 41, where he said, under a certain set of assumptions, we can estimate this thing without knowing much about turbulence at all, just through kind of powerful dimensional analysis and a few constraints, which says that viscosity acts only on things that are very, very small, and you force things at a scale that is very, very big. In between, you can predict what this is. So that's the really crazy part of this theory, and that's one of the few things that people feel fairly confident about in turbulence, even though it's a little bit of an oversimplification in a way we'll touch on a little. Does that make sense to people? So we're going to start thinking about dimensional analysis of this object and a bunch of other things, and we're going to see that that's going to tell us about the possibilities of what turbulence might be, assuming that there is a range in the middle that's distant from the diffusivity and distance from the forcing scale. We're going to be able to describe that. And it's also going to tell us why 2D turbulence and 3D turbulence are qualitatively different. Because when we go to make that argument for those two, we're actually going to find that 2D turbulence has a slightly different set of things to think about. And that's going to tell us that those two classes of turbulence should actually be different. Does that make sense to everybody? So that's what's coming for Friday. And we can also discuss homework problems if people want to start looking at it, but it's probably better to leave that to the next Friday, because we'll talk about Thorpe, and some of the homework problems are on Thorpe and some are on vowels. So take a look at the homework if you want and have questions for Friday, but we'll primarily focus on homework the following Friday. Everybody's very quiet. Okay. Yep. No, go ahead.
10.19.
10.19. How does this work?
Yeah, yeah,
How do we get to this from this?
yeah.
If I plug in this form for U and V and W, I would have a sum over K's, and it's actually, what I want is the absolute value, so it's actually U times its complex conjugate that gives me U squared. If they are not if e to the I kx times e to the I, let's call that number 1, k2x. So this is one of those components. I'm distributing out. So this is infinitely large or very, very large. That is infinity squared large. It's a really big thing you're thinking about. We want to get it down to something less than that size. And the key is if I'm in an integral, if k1 and k2 are not equal to each other, then I get something that looks like which just oscillates. So under the integral, it doesn't give me, it just goes up and down and up and down and up and down, up and down. The only exception to that is if K1 equals K2, in which case I have the integral of 1. And so I get a contribution. So in this potentially very large set of this thing times its complex conjugate, all of the cross products, all of the, if you think of it as a matrix of multipliers, everything not on the diagonal disappears or oscillates. So we only need to worry about the diagonal elements, which means that we can actually bring that inside of a single sum over K. We just run down the diagonal, and then that's this by definition. Does that make sense? Sort of. It's helpful to write it down for yourself with a small number of K's, like just do 0, 1, 2, and write it out and see how it goes. You'll see why, if this is true, if you don't worry about the oscillating parts, you only end up with a very simple form for the energy.
You know, just, yeah.
Cool. And there are deeper worries as well.